So, good morning. I hope you can see my documents.
Good morning. Yes, we can.
Now, here we are going to talk about the parallel plate waveguide. And this waveguide is, of course, what we have been dealing with. That is the transmission line. It has two conductors, and with the conductors in the form of plates. And we can assume that they have a width W that is much larger than the separation of the two plates. So it's shown here for us to see, and it's aligned in the x direction, in the z direction. That is, the axis is in the z direction. We are going to assume a wave that is propagating through between the plates in the positive z direction. So the dielectric between them is epsilon and mu. We are using a separation of B rather than the H that we used before. So H and B are the same. Here, instead of using W, we are going to use a value A. But for now, we are assuming that the plates are of infinite extent in the X and Z directions. So they are assumed to be perfectly conductive. And therefore, as a consequence, there will be no edge effects in the X direction. And we can then consider a TM wave propagating between the plates in the positive Z direction with a propagation factor of the form exponent of j omega t minus gamma z. Remember, TM modes or TM waves have that Hz is equal to 0 and Ez is not equal to 0. And therefore, this is not a TEM wave, but one of the waveguide modes. So at a source-free point in the dielectric, then the axial component of the electric field intensity will be a solution of the homogeneous Helmholtz equation, which is given by the d in the second derivative of Ez with respect to y is equal to kc squared Ez y of y, which is equal to 0, where kc, remember, is equal to gamma squared plus the k squared that we've been dealing with. So subject to the boundary conditions, that at the boundaries, at the inner surface of the bottom and top and top conductors, that Ez of y is going to go to 0 because the conductors are assumed to be perfectly conducting, and we know that the tangential component of electric field's intensity must vanish at a conducting surface. So we can therefore write that Ez can have solutions which have the form En sine kc of y, where n is equal to 0, 1, 2, and so forth. This means, if you recall your physical electronics, then you can start saying that these are the same boundary conditions that we require that the electron plane wave or the wave function have at the infinite barriers. So kc will be given by the value n pi by b, and n is equal to 0, 1, 2, and so forth. So what are we saying by saying that n is equal to 0? If n is equal to 0, we see that Ez of y is going to be identically equal to 0, and we shall see that this is a solution for the parallel plate waveguide because the TEM wave can propagate between the plates. So the other non-zero components of the wave are then obtained from the relationships from the reduced Maxwell's equation, so that the transverse magnetic field intensity will be given by the minus of j omega epsilon by kc squared times the z cross the gradient of Ez, and this we can see is just x cap j omega epsilon by kc multiplied by En and the cosine of kcy. Remember that this case, although it appears k squared here, because we are differentiating that with respect to y, we have a kc that will multiply out there and therefore take out one of the square. So we have only a kc there. And the transverse electric field intensity will be given by the minus of gamma by kc squared times the gradient of Ez, and this is equal to the minus of y cap and gamma by kc En, the cosine of kc y. Now, the propagation constant is going to be expressed as gamma equal to j omega by c and the square root of 1 minus f of c by f all squared. Remember, we say that gamma, that kc squared is equal to gamma squared plus the k squared, where k squared is just omega squared multiplied by mu epsilon, or omega by c all squared. So, and the cutoff frequencies for the different TM modes are going to be given by Fc equal to n by twice b root mu epsilon, and this can be seen to be n multiplied by c, which is the velocity of light, over 2b, and remember b is the separation of the conductors, and this will have cutoff frequencies from n equal to 0, 1, 2, and so forth. So the lowest cutoff frequency, that is the mode, TM mode with the lowest cutoff frequency will be 1, for which n is equal to 0, and you can see that a DC wave can actually go through that waveguide. So the different values of n then constitute the TM eigenmodes of the structure, with the next lowest mode being n equal to 0, or the TM0 or TEM mode. So the mode having the lowest cutoff frequency in a guiding structure is usually called the dominant mode. And for this case, for the parallel plate waveguide, the TEM mode is the dominant mode for that. So an example then. Write down the instantaneous field expressions for the TM1 mode in a parallel plate waveguide. Yes? Is there somebody with a question? Hello? Anybody with a question? So if you don't have any question, please mute your microphone. B, sketch the electric and magnetic field lines in the YZ plane, that is a transverse plane, so to speak. So as a solution, we have seen that the solutions for Ez is going to be given by En multiplied by sine of n pi by b y, okay? And since we are using the first Tm mode, that is Tm1, therefore n is equal to 1, so we are going to replace that amplitude by E of 1, sine of pi by by. Then we multiply by the propagation factor and take out the real part therefrom. And we see that the Ez will have a value of E1 sine pi by by and the cosine of omega t minus beta z. Ey is therefore going to be given by beta b by pi E1 cos pi by by multiplied by the sine omega t minus beta z, and hx is going to be given by the minus of omega epsilon b by pi E1 cos pi by by sine omega t minus bz, where the beta is of course given by that expression there, that is k squared minus the kc squared. For us, the kc squared is the first, the kc for n equal to 1, and therefore we have it as pi by b. So part B, in the YZ plane, E, that is the electric intensity, has both y and z components. And at a given time t, the electric field lines may be obtained from the expression that dy by dz is the same as ey by ez. It's more like looking for the tangent of the angle between the electric field lines with the z-axis. So at t equal to 0, for example, then we can have dy dz is going to be given by ey, y of z and 0, and ez, y of z and 0. And this will give us a value of minus beta b by pi, the cotangent of pi by b, y, and multiplied by tangent of beta z. And this will be the slope of the electric field lines in that plane. We can write this in the form that if you look at that value there, we can write this one as cosine of beta pi by by over sine of pi by by. And therefore, we can write it in the form sine pi y by b over cos pi y by b and multiply by dy, plus, that is, you take this tangent to the other side and multiply the other side with z, and therefore we have separated the variables, that is, those variables, those functions varying only with respect to y, and variables varying only with z. And therefore, we can take the derivative, but what we can say is that if you look at this expression here, sine beta z would be the same as differentiating the cosine of beta z with respect to z. And here, we can see that the sine pi by y by b is just like differentiating the cosine of y with pi y by b and multiplying through by b, okay, with respect to y. So this is what we'll have here. That is, we can always write it as the d cos pi y by b over cos pi by b equal to d cos beta z over cos beta z. And therefore, if we integrate both sides, we'll get an integration of the form the minus of cos, the natural log of cosine pi by by equal to the natural log of the cosine of beta z plus a constant. Or in other words, we can take these values to the same side and we get that cos pi by by cos beta z is equal to a constant for the region 0 less than y less than b. And therefore, since H has only an x component, the magnetic field lines will be everywhere normal to that plane that we are interested in, that is the y plane. But all the electric field lines must obey this kind of function when you draw them. So for the TM1 mode, therefore, we may have that hx of yz at 0 is equal to omega pi epsilon b by pi and E1 cos pi by by, the sine beta z. So the density of the hx lines will vary according to the function cos pi by y by b in the y direction and as sine beta z in the z direction. At the conducting plates, there are surface currents due to a discontinuity in the tangential magnetic field and the surface charges due to the presence of a normal electric field. Remember, the magnetic field intensity, that is the tangential component of the magnetic field intensity, will be discontinuous at a perfectly or conducting surface, and it will be equal to a surface current density. Remember, by the density, we are saying we are just trying to represent the magnitude of h of x at the given position on the line. Okay, so the density will be increasing to show a higher value of h and decreasing to show a lower value of h. So in that form, then we can plot the field lines for the TM mode in the following form. So we are using the electric length along the line in the z direction as beta z, and this is y, and y has been normalized to the plate separation, that is y by b, and therefore we have x going into the page, and then we can see that this would be the whatever the circles of. This is the current or the electric field or the magnetic field intensity coming out of the page and that going into the screen, and the field lines will therefore be shown as shown there. Okay. So example 2. Show that the field solution of a propagating TM1 mode in a parallel plate waveguide can be interpreted as the superposition of two plane waves bouncing back and forth obliquely between the two plates. That is, we can always use TEM modes, that is plane waves, that are bouncing, and they approach the surface, the conducting surfaces at an oblique angle, okay, so that they keep on getting reflected back and forth from the top plate to the bottom plate and so forth. So we'll see that the plane wave will be traveling zigzag through between the plates. So what we can say is that we have seen that Ez for n equal to 1 is given by E1 sine pi by y exponent of minus j beta z. So all we are required to do is to express this sine pi by by in the Euler, in the Euler form, that is using the Euler formula, as the exponent of j pi by by minus exponent of minus j pi by by and divided by twice j, okay, and multiplying those two. And when we do that, this is what we get. We'll get a value of the sine pi by b multiplying by the exponent of minus j beta z. And when we take this one into the brackets, we'll get two components of plane waves. One, we have one plane wave that is propagating in the positive z direction, but traveling in the negative y direction. Because when we multiply this through, we'll get minus j beta z plus j pi by by. And therefore, this would be a value or a wave that is propagating in the minus y direction, while it's going in the positive direction, or in the positive z direction. And the other one, we can see that both of them will be traveling in the positive y and positive z direction. So this is another component, and this is what we were expected to show. And we can see that therefore Ez of y can be given as the sum of two waves propagating in both the z direction and plus or minus y directions, with the phase constants beta in the z direction and pi by b in the positive and negative y directions. So for the TE modes, we have that Ez is going to be equal to 0, but h of z is a solution of the homogeneous Helmholtz equation at a source-free point in that direction. That is, the only thing now we have to deal with is that the Ez is equal to 0, but now the solutions or all the fields in that waveguide will be dependent on the axial component of the magnetic field intensity. And when we do this, we can see that since the tangential electric field component must vanish at the conducting surfaces, then we must have that E of t, that is the transverse electric field component, electric field intensity will be given by j omega mu by kc squared and multiplied by the z cap cross the gradient of h of z. And the normal derivative, remember now we are looking at the normal derivative because the E is related to h as a derivative, therefore we must, and it must go to 0 at the surfaces, then we must look at the derivative of h of z, which must vanish at the surfaces. And therefore, it means that dhz and dy is equal to 0 at y equal to 0 and b equal to 0. This is the same as trying to say that hx or ex or ez are going to be equal to 0 at the surfaces. So thus, a solution of hz is of the form hz equal to hn cos ky with kc equal to n pi by b and n equal to 1, 2, and so forth. We cannot use n equal to 1 equal to 0 like we did for the TM modes, because if we put n equal to 0, the cosine of kcy is going to be equal to unity, and therefore hz is going to be equal to a constant. And therefore, if we take the derivative of h of z, we are going to get a 0, and we'll have no electric field component at all in that waveguide. And therefore, n equal to 0 cannot be a solution for this particular case. So the transverse field components are then going to be given by ht equal to the minus of gamma by kc squared, the gradient of h of z, and we see that as y gamma by kc hn sine kc of y. And the transverse electric field intensity is going to be given by j omega mu by kc squared z cap cross the gradient of h of z, and we get a value of x cap j omega mu by kc hn and the sine of kc y. So the expressions for the propagation constant gamma and the cutoff frequencies are the same as for the TMN modes, because as if you recall from what we talked about. Okay. So from n equal to 0, for n equal to 0, both ex and hy are 0, and therefore the TE0 mode does not there propagate in a parallel plate waveguide. Now, when we are going to get solutions or equations that we'll have to solve will either be the boundary conditions will be given in terms of the functions themselves or in terms of the derivatives of those functions. And this from your calculus mathematics in, I think, third year, is what we call the Dirichlet's conditions, that is when it's just the functions, and the von Neumann conditions when we are using the boundary conditions in terms of the derivatives. Yes?
Yeah, I was asking, would superposition of those solutions also hold? Like a sum of them for the field, yeah, for the HY field that we got.
Yeah, but then that will go against what we assumed in the first place. We assumed our waves are moving only in the positive z direction.
Oh, okay.
Isn't it?
Yeah.
But if you are going to put in reflections into it, then you can put the ones moving in the negative z direction, they will still be solutions. Have I confused you?
I think I see what you're talking about.
Yes.
Mm.
Yeah, we'll see that when we are dealing with waveguides, that the solutions look really, the functions look really very weird, especially when we look at the rectangular waveguide. And therefore, when you start throwing in other things into it, you'll quickly run out of out of pages, and will bury most of the stuff in the detail, and therefore we won't be able to get what it is we are talking about. Here we are looking at the principles. But you are right, the superposition of the waves is also a solution for the equations. So, example 3 then. Write the instantaneous field expressions for the TE1 mode in a parallel plate waveguide and sketch the electric and magnetic field lines in the YZ plane. So we have that h of z is given for TE1, h of z is given by h1 cosine pi by by cosine of omega t minus beta z. Hy is of course going to be given by the derivative of h of z, and therefore we have beta by b 1 over pi, and the h1 sine pi by b of y. I don't think this one is correct. I think it's because of we have only 1 over kc, beta by kc, so we have the b by pi coming in. So, and the h1 sine pi by by, and the sine omega t minus beta z, and h is x is given by that. So the field lines of the electric field has only x components, and therefore will be everywhere normal to the yz plane, and at t equal to 0, we have ex yz 0 is equal to that. Remember, even if I'm just using the t equal to 0, this is just for my own convenience, because it simplifies the expressions. You could take t equal to 10 seconds or t equal to whatever minutes you want to use, but then your equations will look a little bit weird. But since what is true for t equal to 0 is true for t equal to whatever, to 10 seconds or whatever minutes, then we can just use what simplifies our work. And this is what I've seen over the years. Many times when a student is told to try and get a given solution, they always go and look for the most weird thing that just complicates everything. I've seen cases where people also, the Cartesian coordinate system would be simplest to deal with, but then you find them going to use cylindrical coordinate systems, the spherical coordinate systems, and you wonder why. Always make your life easy. Unless you are told to use a particular kind of assumption, then you try to assume what makes that life easy, that your solution as simple as possible. So that is the expression for the electric field intensity. And the magnetic field intensity has both y and z components, and therefore we can always write them in that form. And just like we did in the other case, we are just going to get a value that sine pi by by cos beta z is equal to a constant. And the constant will be lying between minus plus 1. And therefore, when we draw the field lines, we'll see that the E lines are going into the page in this particular case at pi by 2, and they are coming out of the page at 3 pi by 2. And this is informed by this expression that we have here. This is what informs it. You can see that the sine beta z as at pi by 2, this will be unity. And therefore the E fields will be coming out. At beta z equal to pi, this one will be 0. Therefore we should not have Ex anywhere. And at pi equal to 3 pi by 2, this will be negative, and therefore it will correct this value here and give it a given expression. And that's why we have this kind of thing. So this is the electrical length in the direction of propagation, and that is the transverse direction, with our x going into the page, okay? And therefore this will be the minus of ex of yz at t equal to 0, at 3 pi by 2. Now, we talked about group velocity, and we also say that whenever the structure is inherently dispersive, then we cannot talk of a phase velocity there. That is, the different components in the signal will be traveling at different phase velocities. And therefore, we need to define something we call the energy transport velocity in our waveguiding structure. So group velocity is defined as the velocity of the constant amplitude planes on a narrow band signal. And the group velocity definition will then break down whenever we have broadband signals, such as you would get as when we are dealing with pulses of short duration, because one, some of the low frequency components in the pulse will be below the cutoff frequency and therefore will not propagate. We have seen for the parallel plate waveguide, the FC is actually 0, and therefore we have no problem. But for the TE0 modes, which do not propagate in a parallel plate waveguide, those ones will be shorted out. So high frequency components will be propagating at very different phase velocities because of the dispersion, and therefore the wideband signal is going to be distorted. And therefore it means if you start with a rectangular pulse at the beginning of the guide, by the time you come to the output, that whole pulse will be looking smeared out. It will look almost like a cosine or something like that. So we can therefore not define a single value for group velocity in that when we have broadband signals such as those pulses. So we define an energy transport velocity, VE, as the velocity at which energy is transported down the waveguide. So for a lossless waveguide, VE, or the energy transport velocity, VE, is the ratio of the time average propagated power to the time average stored energy per unit length of the guide at a plane Z. That is, V of E is by definition the power at the plane Z, okay, divided by the time average stored energy, which you are calling mu prime average. Now, P of Z is of course given by the integral of the pointings, the time average pointings vector over the cross section of the guide. And this will be given as a half the real part of E cross H star and ds, where S is the transverse cross section. And U average prime is going to be given by the integral over that cross section of the energy stored in the electric field and the energy stored in the magnetic field, which are average values, time average values, and divided and multiplied by ds, that is over the ds of the cross section, and this will give us a value of a quarter of the integral of s into epsilon E star. This is something you obtain from electrostatics, and that will be the magnetic energy density. Okay. So PZ and U average star are calculated for the given propagating mode to obtain the energy transport velocity for that given mode. So example, determine the energy transport velocity of the TMN modes in a lossless parallel plate waveguide. So we have that P average is going to be given by a half of the real part of the Z component, that is what is going down the guide, plus we now have, because Ez is not equal to 0, we have now a component that is going into the conductors. At the top plate, it will be going into the top plate, And at the bottom, this is going to be negative, and therefore it will go into the bottom conductor. Especially if the conductors are not perfectly conducting, then this will represent a power loss in that particular waveguide. Now, if we take the Z component of that P average, then we'll get a value of omega epsilon P by 2 Kc and multiplied by Kc, cos squared Kc squared there. For a unit width of the parallel plate guide, then we can integrate P over the surface, and we'll get a value of, remember the S that we are dealing with is B, which is the separation, multiplied by the horizontal, kind of level. And since we didn't say what the width was, that's why we are taking the width, the plates to have a width of unity. That is per unit width of line. We get a PZ at Z given by that expression there. And we can see that once we replace beta by its expression there, this is what we get. Now, U of E is going to be given by that is the energy density in the electric field, stored in the electric field, is going to be given by that value there, and we get a value of sine squared Kcy plus beta squared by Kc squared cos squared Kc of y. Okay, those are the two components at Ez and Ey. And the energy density in the magnetic field is going to be given by that value there. And here we are assuming that epsilon and mu are real, and therefore we get a value of mu by 2 and multiply by that equation. And hence, when we look for the energy, the average energy stored in the electric field, we'll have to do an integral over a unit with plate, and we'll get that expression, which we can reduce to that expression there. And for the magnetic field, we'll get that expression. And we see that these two are equal, and therefore the energy transport factor is going to be, or the energy transport velocity is going to be given by the average power at Z over the total power stored in the magnetic and electric fields, and we get this value. And we get a value of C squared from 1 minus Fc by F R squared. Now, if we recall from what we talked about the group velocity before, we see that this is exactly the same as the group velocity we defined. And you may ask yourself, then why do we go defining new quantities like the velocity factor? The reason why we do this is because this is only unique for the case where the guide is lossless. If the guide has losses, then the energy transport velocity is not going to be equal to the group velocity in the guide. It's going to be different. And therefore that you can keep in mind. Okay? For the case of lossless guides, the group velocity, that is Vg and Ve, will be the same. And that brings us to the end of that particular point. So any question then, before we continue? Are we okay?
No question.
No question. So I have one of my own. It's do you find my language difficult, or is there a problem? Because whenever I ask questions in an exam, I seem not to be communicating. What kind of difficulties do you find in electrodynamic problems?
I think for some of the problems, the issue is that they usually require too much mathematics, and then doing them within the 2 hours span becomes a bit not possible.
You see that one, you can always see, especially if it's the mathematics, one can see that someone was trying the mathematics. But the problem is, most of the time is that if you find that you have to do a lot of mathematics in the exam, then you are approaching it the wrong way. Because most of the time, what happens is this, if I give you a solution, I tell you the solution of the electric field or the magnetic field in this particular case is this value. I don't see why anyone should go start deriving it from solving the Helmholtz equation. The only thing you have to do to get the other values is now just to use Maxwell's equation with the solution given. Unless I've told you to prove that that is a solution, you don't even need to solve the what is it called, the Helmholtz equation again. Once given the solution, use the solution. Okay, are we together?
Yes, but then now if that happens, it might become also a bit difficult figuring out where the marking points are, because sometimes a 4-mark question will seem to have more
The question
than
is,
the 7-mark question.
the question is, why would you bother about what marks are? Yours is to answer the question, not the marks, is it? Yeah. If I asked you to add 1 plus 1, and I put there 10 marks, I don't ask you to starting to think about how you can get 1 plus 1 now. How do I get that 10 marks? That's not your problem, is it?
True.
Yeah, so I hope you guys are going to learn, because even in the industry, once you start working in the industry, it doesn't mean that you'll get more money if you make the solution more difficult. Okay? You need to give the client the solution that is easiest for him to implement and is functional. And you also want to minimize the amount of money you have to use in providing that solution. So the idea is not to worry about how the marking scheme looks like. The idea is to look at the question and understand it, and then solve it the way you understand it. Don't think about now putting other things so that you can gain more mark. So anyway, that was by the way. So we'll now look at what we call the rectangular waveguide. And the reason I started with the parallel plate waveguide is because I want to show a particular case here. Now, parallel plate guides, we have already said that we assumed in the first place that they had infinite extent in both the x and the z directions. But in many cases, the width of the plates is not going to be infinite. It's going to be finite, just like we saw for the parallel plate transmission line. We gave it a width of W. The only thing we required is that W be much larger than the plate separation. So in practice, the plates of the parallel plate transmission line will have finite width. But if they have finite width, we can place, if you look at the infinite parallel plate transmission line, we can choose somewhere along the parallel plate, in the x direction, we can choose points where the electric field will be everywhere equal to 0. And we can place there short-circuiting plates, okay, and without changing the distribution of the electric field between the plates. So this is what has been done. Now imagine this was a parallel plate that is at the top and the bottom plate. They were of this infinite extent. Because we have seen that whatever the fields are sinusoidal in that direction and sinusoidal in the direction of propagation, we can choose where the E becomes completely 0, because the sign will always be crossing the 0 line, and therefore place a plate that is perfectly conducting and we'll get one like that. And another one where the field is also 0. And we'll have the same kind of field distribution in this empty space that we have in here. So this would be the plates of the line of the guide, and that, and this would be the shorting plates which we have now put to develop a sidewall for that. And this develops a hollow or a rectangular pipe. Rectangular in the sense that it has a height B and a width A. In many cases, we'll find that A will be made longer than B for obvious reasons, which we shall show. Now, the thickness of the plates is of no consequence to us, especially if we assume that the walls of the guide are perfectly conducting. The skin depth is going to be 0. But if they were finite conductivity plates, then we'll have to make sure we'll always assume that the thickness of the walls is large enough, much larger than the skin depth for that particular frequency of interest. And therefore, in other words, you can only deal with the inner dimensions. And that's why I've shown that the B is the inner surfaces of the top plate and the bottom plate, and the A are defined with the inner surfaces of the two side walls from at x equal to 0 and x equal to A. The Z is in this case pointing into the page. So the rectangular hollow waveguide is the most widely used waveguide in the frequency range between 320 megahertz to 330 gigahertz. So the cross-section dimensions for most typical guides that you'll be getting in the industry would be the WR2300, which operates at 320 megahertz and has an A of 23 inches and a B of 11.5 inches. If you want to change that one into the SI units, just multiply that one by 25.4 millimeters and you'll get it in millimeters. The WR3 operates at 333 gigahertz and it has an A or a width of 0.864 millimeters and a height of 0.432 millimeters. And the WR90, which operates in the frequency range 8.2 to 12.5 gigahertz. If you recall from our electromagnetic spectrum that we talked about, this is usually called the X band, and it has a value of 2.286 centimeters and a B of 1.016 centimeters. If you look at this A and B, the relationship is very close to what you'd call that A is twice B. And this is by design, because we shall see when you want to drive your waveguide with only a single mode propagating down that guide, we'll want to make sure that the frequency, the cutoff frequency of the next higher mode will be higher than the value of the frequency that you are dealing with, okay? And therefore, that is, it will be outside this bandwidth here. And therefore, the guide will only propagate only one value, okay? So, the WR90 waveguide is a standard for the applications in the X band. So, TEM or E modes propagating in a hollow rectangular waveguide. So we are going to assume that the guide walls are perfectly conducting and the enclosed dielectric has parameters mu and epsilon. Remember, if it's going to be hollow, that mu is going to be that of air and epsilon will be that of air. And this is what you'll get most of the time. But for now, we are just using the general form where we have a dielectric. Then we can specialize that when the epsilon is epsilon naught and the mu is mu naught. So at a charge-free region in the dielectric, Ez, that is the axial component of the electric field intensity, will be a solution of the homogeneous Helmholtz equation. But now we are not going to use only one single term here because we have now finite extent in the x direction, finite extent in the y direction. But in the z direction, of course, is in the direction of propagation, and that will be k. This is not kc squared, this should just be k. And dz equal to 0, subject to the boundary conditions at the tangential electric condition that the tangential electric field components vanish at the conducting walls. So we'll assume that Ez can be expressed as a product of one-dimensional non-zero analytic functions of the form Ez equal to x of x and y of y, and this we invoke or we suppose is not going to be equal to 0. That is, we must insist that it cannot be 0. Remember what I said, this is a slight problem here. This should be just k, not kc, so that d2 kc squared plus kc squared there will be equal to kc. So this whole thing should be kc. This problem, okay, is an error there. So now once we throw this into the Helmholtz equation, we can see that now the two components, that is the x derivative and the y derivatives, separate out, okay? And the only reason this can be equal to minus kc squared, which is a constant, must only be because this term is equal to a constant, and that term is equal to a constant, so that the sum of the two constants is equal to minus kc squared there. So this means that each of the terms must be separately equal to a constant, and we can say that 1 by x of x d2 x of x by dx squared equal to minus kx squared, and the other one is equal to minus ky squared, as long as kc squared is equal to kx squared plus ky squared. That must be fulfilled. And you recall that this one is the same thing we dealt with when we were talking about the physical electronics, as well as the last semester's solution to the Helmholtz equation. So kx and ky are called separation variables, and therefore we can write those components in that form. So we have a Helmholtz equation in the x direction and a Helmholtz equation for the y direction. And the boundary conditions then require that Ez equal to 0 at x equal to 0 and x equal to a, and 2, it must be equal to 0 as well at y equal to 0 and y equal to b, because Ez is everywhere tangential to the walls, okay, at x equal to 0 and x equal to a, and y equal to 0 and y equal to b. And therefore, we must have that x of x must be a sign given by xm sine m pi by ax, where m is equal to 1, 2, and so forth. We cannot use m equal to 0 in this particular case because of this sign to make x of x equal to 0. And y of y equal to yn sine n pi by by, n equal to 1, 2, and so forth. This is by convention that the width will be given the m, and the height will be given, the y direction will be given the n. If you recall your physical electronics, these are like the quantum numbers that we were talking about, and the principal quantum numbers. But for now, just look at it as they are. They will be the mode numbers in this particular case. And therefore, since we say that Ez of x and y is equal to x of x times y of y, we therefore have a value of emn sine m pi by a x sine n pi by by for m equal to 1, 2, and so forth, and n equal to 1, 2, and so forth, where emf of n is equal to xm and yn, and we can is the amplitude for the particular mode mn, and the kc squared we can see is going to be given by m pi by a all squared plus n pi by b all squared, because this is kx squared plus ky squared, as we already saw before. The transverse, the transverse field components for the propagating modes, okay, and remember we defined propagating modes for which gamma is equal to j beta, so, or the f operating frequency is above the cutoff frequency, then these will be the functions given here as the transverse component of ET equal to the minus gamma by Kc squared and del of T Ez. Remember the Hz is equal to 0 for this particular case, and therefore we have that kind of expression there. And we also have a Y component with that value. Now, for the guy who was asking about superposition of the waves now propagating in the minus Z direction, then you can see now the weirdness that will appear. Now, we already have two components that we have to deal with, that is the X component and the Y component. Now, for the case of Z with the positive Z direction, and then we have to multiply it by the similar values in the other direction, so to speak. So the transverse magnetic field field intensities will be given by that equation, and also we have two values. Remember, okay, we have two values of the X component and the Y component, where the beta is of course given by K squared minus Kc squared, which is omega by C root 1 minus Fc by F all squared. So for a given TMN mode, the cutoff frequency is then going to be given by, remember the cutoff frequency is from Kc, and Kc is omega C divided by the C, and therefore once we put that, we'll see some value of C by twice pi root of m pi by a squared plus n pi by b squared, and we can always factor out the a out, and we'll get a value of C by twice a, that is twice the width of the guide, the square root of m squared plus n squared into a by b squared. Or alternatively, we could look at the cutoff wavelength of that mode by taking that, by dividing through, that is remembering that f multiplied by lambda is equal to C, and we can get a value of 2a by m squared plus n squared into a by b all squared. Now, one thing we can say is that neither m nor n can be 0 for the TM modes, because the Ez is a sine function, okay? And if any of them is 0, it will make that Ez equal to 0. And therefore, the lowest cutoff frequency, that is the frequency the lowest, is when m is equal to n equal to 1. And we call it the TM11 mode for any given guide of width A and width and height B. So before we continue, what I want you guys to do is to use a guide, say for the X band guide, that is the WR90, okay? Assume that A is approximately twice B, so use the value of B, okay, to get the value of A by multiply by 2, and then draw or give a table of the cutoff frequencies in terms of the fundamental or the dominant mode frequency C by A for m varying from m equal to 1 to 4 and n equal to 1 to 4. Put it in a table, okay? Then you'll see what happens. So example 1, write the instantaneous field expressions for the TM11 mode, hence sketch the electric and magnetic field lines in a typical XY plane and a typical YZ plane in a waveguide with cross-section dimensions A and B. So you can see the weirdness of what we are talking about. Now we have we have 5 field components. So the X component is obtained from what we had there, and all we did was to multiply that one with the propagation factor, which is the exponent of J beta Z, and we get a value. And the Y component, I think this one is a problem here, it's not Y, there should be a Y here. And then we have, this is the EY, is a is a typographical error there. And Ez is what we have already solved with the values of E11, that is Mn, and given by that value there. And Hx is given by that, and Hy is given by that. So all you need to do is what we have already solved and multiply it by the propagation constant, which is exponent of j beta z, and take the real part. So beta is given by that value, and in a typical xy plane, the slopes of the electric and magnetic field lines will be given by that dy dx for electric field is a by b tangent of pi by ax cotangent of pi by by, and dy dx for the h of the magnetic field is going to be given by minus b by a cotangent of pi by ax and tangent of pi by by. Again, this we can always rewrite them in the form that we saw before for the parallel plate guide, and then use integration. So we note the following, that when we multiply dy and dx of E and dy by dx of H is going to be equal to -1. And that is, it means that both the electric and magnetic field intensity lines are orthogonal. They are equal, they are at right angles everywhere in the xy plane. And the E lines would be normal, and the H lines parallel to the conducting guide walls in a given YZ plane. Say at x equal to a by 2, or sine pi x by a equal to 1, and cosine pi x by a equal to 0, then we have that dy dz is going to be given by that equation there, and H has only an x component. So the field lines for the TM11 mode are then illustrated as illustrated. That is, when we are looking down the guide, the electric field will be, the magnetic field will be seen to be circular, all right, around that plane, and the field lines are going in and then going towards. Once they go in, they go parallel to the guide and then go back towards the walls. And since the walls are perfectly conducting, they must always attack the walls at a normal incidence. For the YZ plane, we get a similar kind of variation as we had before. And this is how they look for that particular case. So for the TE modes, I don't know how much time I have. And I think my time is up, so I'll stop at that, TE modes. Then we can attack it from there tomorrow.
Okay, and so there's some recordings you haven't sent. That's for 3rd, 17th, and 18th.
Yeah, those ones I'll give them later. We just they usually come late, but then I usually find myself not going to the internet very often because there are other things I'm doing. So, but I'll avail them as soon as I get into the net, like just a few minutes after this.
Okay, that will be really helpful. Thank you.
So anything else? And I remember you have also the class notes to read. You can use the class notes as well. Don't just base yourself on the slides and the whatever the lectures. I've given you even a number of books in which you can always, avail yourself to. Okay, electrodynamics requires a lot of practice. Okay, because you'll see that most of the problems that we'll be solving, they are just repetitive, so to speak. And therefore, if you have seen them before, or if you have seen a similar situation before, it becomes very easy for you to solve. So with that then, if there are no questions, then I'll wish you a nice day, and we will meet tomorrow. Is that okay?
That's okay. Thank you. Yes.
Okay. Okay. Goodbye then.